Hey everybody, welcome back. Today we're going to be covering the thin lens equation and magnification. What you need to know before watching this video is a general understanding as to what the focal point is, what the focal length is, and the differences between convex and concave lenses. I want to start by reminding you what a ray diagram is. What the text says is a ray diagram is a visual representation of the relationship between an object, the light rays that are coming off of it, the lens, and the image that is formed. So on the left you have a ray diagram for a convex lens creating an inverted image, and on the right you have a concave lens creating a upright image but a smaller image in between the object and the concave lens. Now what I want to show you is a simulation that relates the object with the image. Now what I just want you to observe is what happens when I move the object on the left. So this candle here is our object, this candle here is our image, and we have a converging or a convex lens right in the middle. Now just to remind you, f means the focal length, 2f would be 2 times the focal length, 3f would be 3 times the focal length, so on and so forth. So what I want you to see is, watch what happens as I move the candle back and forth. So starting at 2f, when it's at 2f, the image is also at 2f, just on the other side and upside down. When I pull it back further than 2f, the image gets smaller in height and it gets closer to the lens. If I move the candle closer to the lens, the image gets larger and further from the lens. So what I want you to notice is that the distance between our object and the lens is related to the distance between the image and the lens. Also note what happens if I drag this f here and change the focal length of the lens. So if I increase it, my image is getting further away. If I decrease it, my image is getting closer. So the point I'm trying to make is that there's a lot of things that are at play here that are all related to each other. And a similar thing can happen with a diverging lens. So if I move the object, the image is also increasing in size, getting closer to the lens as I get closer, getting further away from the lens as I get further. And if I change the focal length, that also is a variable that changes where the image will be. So the point I'm trying to make is that for both lenses, the 3 things that are at play when considering where the image will be, the first thing is the focal length of the lens. Now that means, where is f in relationship to the lens? How far away is the focal length from the lens? Now the focal length of a lens will just be dependent on its geometry. How thick is this lens? How big is this lens? That will change the focal length of the lens. What we're going to refer to that is as f, small f. Now the second thing that comes into play is how far the object is from the lens. So this distance here. What we're going to call this is p. So this distance is lowercase p. This is the distance from the object to the lens. And lastly, the distance from the lens to wherever the image is formed. So for example, on a convex lens, the image may be formed over here. This distance will be referred to as q. For a concave lens, we know that the image will be somewhere inside, just a little bit smaller. So this distance here would be the q. So 3 new letters that we're assigning to things. F is for the focal length, P is for the distance from the object to the lens, and Q is the distance from the lens to the image. Now this is for both types of lenses, it doesn't matter which. One thing to note before we move forward is that when the object is to the left of the lens, the focal length here is to the right because that's where the light converges to. So because it's to the right, our f numbers will be positive. And for a concave lens, because the focal point is behind the lens, it's to the left of the lens, our f's will be negative. Let's just try not to forget that when we solve a few problems in the next bit. So right here is what's called the thin lens equation, and what it does is it relates P, Q, and F. What it says is that 1 over p, the distance from the object to the lens, plus 1 over q, the distance from the image to the lens, equals 1 over f, the focal length of the lens. Now let's try to use that to solve example 1. Example 1 says, an object is placed 30 centimeters, there's a D, 30 centimeters in front of a converging lens with a focal length of 10 centimeters. How far from the lens will the image form? So we're given a few pieces of information. I'm just going to highlight them. So the object is placed 30 centimeters in front of a converging lens, and the focal length is 10. And what we need to do is find how far from the lens will the image form. So I'm just going to draw a small little diagram. Here is my converging lens. This will be my middle line. This will be my object here. I'm going to label the distance that the object is placed from the lens as 30 centimeters. It also says that the focal length of the converging lens is 10 centimeters. So I'm just going to draw a little f here and say that this is 10 centimeters. I did it to the right because that's where the light focuses in a converging lens. Had this been a concave lens, I would have drawn it to the left. Now what they want to know is how far from the lens will the image form. Let's just write our given values. So given, I know that the object is 30 centimeters from the lens, which is my P. So P is 30 centimeters. I know my focal length is 10 centimeters. And I need to solve for how far is the image going to be. So that's Q. Let's write the numbers in for our P, Q, and F in our equation. So I'll just start by writing the equation. 1 over P plus 1 over Q equals 1 over F. P is 30, so we'll continue down here. 1 over 30 plus 1 over unknown value Q equals 1 over 10. 1 over 30, we'll just calculate that in our calculator, is 0.333 plus 1 over Q, and 1 divided by 10 is 0.1. Now we're going to subtract the 0.333 over, and before I do that, I need to fact check. Sorry, it's 0.0333. I thought I had that wrong. So we're going to subtract the 0.0333 over to the other side. So 1 over Q equals 0.1 minus 0.0333. 0.1 minus 0.0333 gives you 0.0667. So we'll just continue over here. 1 over Q equals 0.0667. Now the last thing we have to do is just cross multiply. The Q will come over and the 0.0667 will come under. So let me just show you that. 0.0667 equals Q. So 1 divided by 0.0667 is our Q, and it's very, very close to 15 centimeters. When your Q number is 15 centimeters, that means the image of the upside down man will be 15 centimeters away from the lens. That's how you use the thin lens equation. Let's do this once more for a concave lens and just see how it plays out a little bit differently. So here what it says is, the same object is placed at a distance 12.5 from a diverging lens, or a concave lens. It has the same focal length as the lens from example 1. Find the distance between the image and the lens. So because we have a diverging lens, it's going to be drawn like that. Here's our little center line. Here's our man. He is at a distance 12.5 centimeters. And because this is a diverging lens, it says the focal length is the same as the lens from example 1. It was 10 centimeters, but we're not going to draw it to the right. We're going to draw it to the left. So here is my F. 10 centimeters. Because it's to the left, when we put this number into our equation, we're going to put it in as a negative. So let's do our given list again. My f, this time I'm going to write it as negative 10 because it's a diverging lens and the focal length is behind. So because it's behind, we're going to say negative. The object distance is 12.5 centimeters this time. And what we need to solve for is the image again. So let's just write out the equation. 1 over p plus 1 over q equals 1 over f. Now I'm just going to put the numbers in. So 1 over 12.5 plus 1 over unknown q equals 1 over negative 10. Now I'm just going to do this math now. So 1 divided by 12.5 gives you 0.08, and this gives you negative 0.1. What I'm going to do is subtract the 0.08 to the other side. So what I'll get is 1 over q equals negative 0.1 minus 0.08. That will give me negative 0.18. Last thing to do is just to cross multiply both sides. So negative 0.18 comes here, q comes here, and if we do 1 divided by negative 0.18, we get negative 5.55 centimeters. Now the sign here is important because negative means it will be to the left, which makes perfect sense because we know that's what will happen for a diverging lens. We'll get a little man to the left of the lens at a distance negative 5.55 centimeters. So over here, our image is to the right. We got a positive q number, makes perfect sense, and we used a positive number for focal length because it's to the right. For a diverging lens, we used a negative number for our focal length because focal lengths for diverging lenses are to the left, and our image is to the left, and that's why we get a negative number for our q. So everything is perfect, everything makes sense here. Now there's one more thing that we haven't talked about yet, and that's when we're playing around with the distances, what we haven't accounted for in our thin lens equation yet is how much bigger the image is getting. Okay, there's no variable inside the thin lens equation to account for how much taller the image is as compared to the object. So for both kinds of lenses, the images either get smaller or larger, but the thin lens equation doesn't account for that. So lucky for us, there's another equation that does. It's called the magnification, and what magnification is a measure of how much larger or smaller the image is compared to the object. So the equation is just kind of simple. It's big M stands for magnification, negative Q over P. And I'm just going to fact check that real quick. Yep, that's right. So M is negative Q over P. Q is still the same as it was before. P is still the same as it was before. M stands for the magnification. So let's try it with the lens image combinations from example 1 and 2. So I'm just going to peek over at 1 and 2 to see what those numbers were again. So P was 30 and Q was 15. So for example 1, P was 30, Q was 15. And to calculate the magnification, you just do negative Q, which is negative 15, over P, which is 30. What we'll get is negative 1 over 2. Now let's talk about what that number means. The negative here means that the image is upside down, which makes perfect sense because that's what happens in a converging lens. Now this number, maybe it's better to write it as 0.5. This number tells you how much smaller the image got. So 0.5 means that the image is half the size of the object. So this means that in example 1, our image, our little man on the other side, will be half the size of the actual object. Let's do the same thing for the numbers from example 2. So example 2 had a Q of negative 5.55 and it had a P of 12.5. So to find the M, we put a negative because that's in the equation. We had another negative for Q. Those negatives will cancel out in just a second. And we'll put it over 12.5. So let's do the math. The negatives cancel with each other. We get a positive number. I'll just put this in my calculator real quick. 5.55 divided by 12.5. If we do that, we'll get 0.44. Now let's talk about this number again. This time it's positive. Because it's positive, it means that it's not upside down, which again makes perfect sense because for a diverging lens, you don't get upside down images. And because it's 0.4, this means that it's 0.4 times smaller than the object. Now, in these examples, we had both of the examples, the images got smaller. But I'm just going to summarize it for you. When it's negative, the image is upside down. If it's positive, it's just the right way up, so I won't write that. If the number is greater than 1, that means the image is bigger, so the image got magnified. If the M is smaller than 1, then the image got smaller. So the image is smaller than the object. So this is kind of the summary for when it comes to magnification. Now let's check for your learning. First question is, what is the thin lens equation? Let's see if you can remember it off the top of your head. Second is, what is different about a concave lens when using the thin lens equation? Third is, what does magnification tell us about the image? Now to summarize the video, the thin lens equation relates the object distance, image distance, and focal length. Its equation is 1 over P plus 1 over Q equals 1 over F. The magnification number tells us how much larger or smaller the image is, and it also tells us whether or not it's inverted. So there were 2 new equations in this lesson. They're very simple though. If you have any questions, shoot them at me. I'll try to get to them. Otherwise, thank you for watching.